Shit, I was muted all this time. I was talking. I've been talking crazy, crazy. Okay, I gotta do a little bit of setup, and then I can turn the camera on. No, you never want to turn the camera on too early. Things might happen that you really don't want to happen. Bad stuff. Oh, I got a follower. Wait, please try again. Looks like you're trying to log in from a new device or location. Is a security measure? What? Oh, I can't read. Okay, I see. Trying to log into Twitch on my phone so that I can have the chat in front of me. Give me a second. I'm very bad with computers. Online computers are... Oh! I'm inside. Allow notifications. Whew. What are we doing? Alright, how do I... So, okay, I'm live. How do... Oh! I see the chat. Okay, test. No, I don't want ads. Alright, it works. Woohoo. Okay. Ha ha. Perfect. Now I can, turn on the do not disturb and whatever. Have the phone next to me and how do... Oh. Okie dokie. 1 second. Gotta turn on the... I gotta fly over here. Alright. Until tomorrow. Hello. What are we gonna do today? So I got some feedback that I gotta talk louder, that I have to have a cup of tea and all that. And explain what I'm doing and whatever. Alrighty. What are we doing today? You can see my screen, right? Yep. So. We're gonna pull up VirtualBox. Let's see. It's a good evening. In this part of the world. The vibes are good. Vibe check. I can collapse this. Visual Studio, got some C code over here. Alright, let's get into the VM. Now I'll explain what I'm doing. Actually, I actually don't know what I'm doing. This is all improvisation. This is not like people who make websites they've made many times before live, and it's all tested. This is all improvised. Let's collapse this. What are we doing? I'm waiting for someone to hack my 127.0.0.1 server. Wouldn't that be crazy? Haha. Right, anyhow. What are we doing? Okay, so I'm learning how XDP works and what packet processing options there are in Linux and whatever. So yeah, I was trying to figure out how XDP works a while ago and I couldn't, so I started, I figured out some of it, but couldn't really do it well. So I decided to do this little tutorial on GitHub. Where's my friend who told me he's gonna come watch? Where's my friend? 1 second. I'm gonna tell him we're in the middle of a very productive coding session. Hurry up. All right. Okay. Who's left to join? Who are you? All right. So I decided to do the lessons over here. And last time I was doing did the basic lessons all in one day, and then I was doing basic 404 during the stream, and then I couldn't figure out something in the end, which was a minor issue. So the idea is to write some very limited C code that we can then compile to eBPF, right? Is that the correct term? And load it as an XDP hook, so that every time a kernel gets a packet, it executes our Turing incomplete code to process it. Namely, it's going to be supposedly way more efficient than if we wrote just some user space code to pull up all the packets into user space. So we essentially extend the kernel in a very, naive, simple way. So that's what we're going to do. And what did I do last time? So last time, what was it doing? I was doing this thing. So if you're writing a program that's gonna be run by the kernel as a mini virtual machine, you're gonna have problems communicating with it. And eBPF expects you to use these data structures called maps, so that you can write your own loader or whatever and load the eBPF program into the kernel and communicate with it via map. And that's pretty cool, but the problem is that, let's say you had one program as a loader, which we have over here, and then another program which, for example, like pulls some information from the map and then does output some statistics. Then the stats program wouldn't know how to figure out where to get the map from. So what were we doing last time? We were overcoming that problem. Ha ha ha. No funny. Right. And how did I do that? Okay. So what we do is mentioned above, the XDP stats tool will not detect if XDP loader loads new maps and new BPF programs, and will need to be restarted. Okay, so every time we have the loader and it restarts, it creates a new map by default, which is not like, that's fine and it makes sense intuitively. Let's say we have a program that wants to pull up statistics from the kernel, and then if we reload the program, it's pretty intuitive to expect for the stats to reset to 0. But the program that is the observer wouldn't know that the data structure it should be looking at is the new data structure, like it wouldn't know what's pointing to it. So the naive solution is to reopen the pinned map file each time. But how do you detect that the file changed? If you don't detect when dealing with a new map, then the stats diff when 2 measurements will be negative. Think about solutions where you remember the ID number to detect changes, either via the map ID or XDP program ID, and that's what we did. So in XDP stats, we did this little thing where we what's it called? Every time we needed to pull the map with the data coming from the kernel, we checked if its ID is equal to the expected ID, and if not, we sort of reloaded it, restarted the statistics program. But now there's a better way to do it, as they tell us in the second assignment. As mentioned above, eBPF can reuse and replace a map with an existing map. It just requires, what does it require? Write in your own BPF progload or BPF progload accent. So that means we just need to, so when let's say you wanted to restart your kernel program, so you do it via this loader that we wrote. Now the problem is that we want to reuse the old data structure that's being used for communication between, it's not data structures, whatever, between the kernel and the user space. And what we did to facilitate that is what did we do? We essentially pinned the map to the file system so we can reuse it between the instances of the loaded program. So every time we run, we pin the map, and then the next time when we run, we can check that there is a pin map and we can reuse it if it already exists. So that's pretty good. And I had minor problems last time, but now we can check that it works. How do we check that it works? So what we're gonna do is get into share to do cd XDP tutorial cd basic 04 make XDP loader. It's not gonna work, but let's figure out how to make it work. So we need to do sudo, we need to do device test, and we need to do force because if there is a there is no such device because we got created. And to test all this, right? So to test all of this, we need some network interface. We need a network interface that we can attach this program to, the kernel program to. So every time the network interface gets the packet, our code gets run. So for that, there is a little script included in the lesson so that we can create what's called the namespace, Linux namespace, and it's connected to the default namespace with two VIFs, virtual interfaces, the outer one and the inner one. So what we're gonna do is create a namespace and then ping the outer end of the pair, VIF pair, from inside the network network namespace. And then on the outer side, we're gonna load our program and observe the packets or whatever. So let's do this. Oh, I don't want to call it. No. I don't know. What are you doing? Oh. No. All right. Setup, name, test. All right. There we go. All right. There we go. So we got our, we can look at if config. The outer address is right here. Then what we're gonna do is we're gonna get inside what? Yes, we're gonna get inside the namespace we just created, and for that we need to do something like, I think we need sudo again. Sudo ipnet ns exec. Oh, that's the name test, but that's, I'm not sure. Let's I don't remember. There we go. Exec bin bash. There we go. All right. Let's see. Okay. So now we have our network interface. We can load our program. Let's run the loader. Let's sudo this thing. Let's do device test test interface. Then let's force it. Let's also what error finding proc section. So this is because if we look at the program itself, we have a bunch of so within one sort of C file, we can declare as many programs as we want, and they're all when we're attaching them to they all get compiled, and we get one ELF file. But then when we attach it to the network interface, we need to specify which program exactly we're gonna. And here we have three simple programs that either drop a packet differently, or pass the packet. So we're gonna pass it for now. What's it called? All right, success. So now if we look at IP link, we see that there is an XDP program attached. Success. That's what I call success. What are we gonna do now? Now we're gonna ping the outer pair. Let's see. Now if we load our XDP stats, it should work. What? Will this work? Yo! Woo! It works. We see the packets coming in. We see the delta. We see the total number of packets every second. We see 1 packet per second. We're sending ICMP packets and we're capturing them here. You know what? We're gonna make this ICMP program fail. You know why? Because we're gonna reload and say XDP drop, and now we're gonna be dropping the packets, and we're gonna run XDP stat. And now when I send ICMP packets, I don't hear back because we're dropping the packets. But anyhow, I don't want to do that. Let's not drop anything. So the program we're going to load is this. Okay. So this is sort of the kind of stuff we were doing the last time, but where's my friend? Where's my friend? Oh, I think he's dying or whatever. It's a good Sunday. Oh, it's not Sunday. It's a good Tuesday. I had an abstract algebra exam today. All right, so what are we gonna do now? Now we're gonna move on to the little bit more advanced lessons, packet processing lessons. Once you have the basics figured out and know how to load programs into the kernel, you're ready to start doing what? Second, pulling up the chat. The chat with one person, Jinyao. Haha. Processing some packets. The lessons in the packet processing category will teach you about the different steps needed to process data packets, including parsing. All right, let's get to it. If anything, we have the solutions. All right, what you learned. This looks long and complicated. You know what? We're gonna work until my laptop dies. Wish it were an M1 chip laptop, but you know, we're not that lucky today. So runs out of charge pretty quickly. We will use the loader from the basic 04 lesson, the main file in this direct rule to copy it over to this direct. So you're gonna after running make the test. Yeah, let's do that. CD packet 01 make. Cool. The test, and you will use this when run with the load command. Example below, we assume you've installed the ALSIF. No. All right. Will execute arbitrary programs. Crazy. Security through obscurity is my favorite method of doing things. So long, you learn in this lesson. This lesson will teach you how to parse packet data from XDP. This is done by direct memory access using pointers to the packet data. That's a joke. Which one of the reasons for the high performance attainable. Oh, that's cool. This works because the kernel verifier will check that all data access are within the packet. That is also nice. So see, we have all this verification from the kernel, so we know we're not like you could imagine your first guess as to how to write this efficient packet processing code would be probably to write a kernel extension, but that would never be as safe as writing eBPF code. This works because we'll see how it works. The packet verdict program return code based on the packet data. We'll cover how to structure the packet parsing code. Readability and code reuse. They're gonna teach us best code practices. Points to be aware of while completing the assignments listed below. The data. The data and the XDP program is executed. The receiver is a parameter pointer to a struct. Yep, which contains context information about the packet. The subject is defined in BPF8.h. Yes, the last two items in this correct. Oh, that's interesting. What is this? There's data fields which contain the if index or XQ index that the packet was received on. All right. How? I see. Interface index. The first three items are actually pointers, even though they're defined with the data field point to the start of the packet. The data field points to the the data meta field points to the metadata area that XDP programs can use to store extra metadata to accompany the packet. Where are our viewers? Where are the followers? Where are the thousands of people? And this lesson we will only be working with the data and to the meta. That was loud. Anyhow, verify we rewrite the pointer access when the program is loaded to point to the actual packet data, but to satisfy the compiler type check, and we need to cast the fields to pointers when accessing them. Okay, the packet that we're gonna do. Oh yeah, this is here. It's just a shared folder. Right. Okay, we're getting into parsing. This is our we have the loader copied into here, and which we've verified that works, so it doesn't look that bad. Packet bounce checking. As mentioned above, packet data is accessed. What is it converted in U32 to a pointer? Where do you mean? Do you mean this or this? Because we need to compile it first, and otherwise the compiler is not gonna like what we're doing, because we need the pointer type, right? Is that true? Packet. Let's read the sentence again. But to satisfy the compiler type check, and we need to cast the fields to pointers when accessing them for this reason. Yeah, what would happen if we were just U32? I don't know. Not sure. What do you think? That's a serious question. Oh, why is it only 32 bits? That's a very good question. I actually was thinking the same. I have no idea. That I'm clueless about. BPF, why 32 bits? What if BPF 64? eBPF. What? Let's see. 64. Oh, not 65. 64. The ability to run the. Oh, see. Oh, okay. So I guess that's so they call the thing that you load into the kernel. They call it the mini virtual machine or something. For one, the design of the virtual machine and its instruction set architecture were left behind as modern processors moved to 64-bit registered and invented new instructions required for. No, that's the BPF. That's the predecessor of eBPF. Okay, they more closely resemble contemporary processes, allowing BPF instructions to be mapped more closely to the hardware ISA for improved. The most notable changes was a move to 64-bit. Cloudflare. Who's Cloudflare? Never heard of them before. Operation because in pointers are 64-bit. No shit. Right. That's it's gonna be one more question for myself. Anyhow. used by the program and look for comparisons with. Oh, interesting. Well, the verifier performs a static analysis at load time and will track all memory address offsets used by the program, look for comparisons with the data end pointer, which will be set to the end of the packet at runtime. This means that if the program does something like this, the verifier can know that all instructions in the true branch of the if statement can safely access the first 10 bytes. So if a program does attempt to access the packet data in the else branch, the program will be, yeah, it's pretty fun because it's not even Turing complete code. You're I don't know, dude. You do the compiler stuff. What I know is that you can't even write infinite while loops because you can't have infinite loops. It has to have finite execution time, right? Well, yeah, that's a question for you. That's a question for you, how they do that. The compiler person. I guess not. No. No. So when I nope, I don't think so. There's a part where we inspect the ELF file. Let's do that. I don't remember how to. So let's give it a. Oh, there we go. All right. Compiling. You should. Turns this restricted C code into BPF bytecode and stores it in an ELF object file named. Right. So in our case, oh, we do have that. Whoa. You know what? I don't know how to look at this. What do you think, Genia? When going through a packet and parsing subsequent headers, it is generally necessary to keep track of the current parse input position. When using helper function to parse packet headers, those helper functions generally need to modify the current parser position. And pointers to what? Cursor. All right. All right. It's actually pretty old. BPF, Berkeley packet. So the original version of this was, when was it created? In 2007? No, that's an edition. I don't know. History, 1992, the original paper. But this is the, we can write loops, but I don't think we can write infinite loops. But also, I haven't gotten that far. There has been no need for a loop yet. So we'll see. Loops, eBPF. Are loops allowed in Linux as BPF? Have now landed to bounded loops have now landed to the kernel and are available starting with Linux 5.3. Well, I guess you would have to signal to the compiler somehow very, very distinctly that the loop is finite. But at the original time of the answer, the loops were not allowed at all. there are two. No, we don't want workarounds. Yep. All right, what are we doing? Our assignment. The end goal of the session is to build an XDP program that will inspect packet headers, drop every other ICMP echo request, every other, that's cool, packet seen on the interface while allowing everything else to pass up to the kernel. Oh, that's cool. We're going to identify ICMP packets. That's dope. So we're going to look at the IP packets. The assignment below will gradually build up towards the goal. The starting point for this assignment is the packet parsing program, which will parse the. But let me think. All right. So we have the right. We'll extend this program by adding new features. The program includes. I know it's good stuff. I knew you would love this. I know people have a taste for good coding stuff. However, we haven't written a single line of code today yet. It's been half an hour. Right, let's get to it. What's the status helper from basic coding? To monitor, use tstats to run the stats. Tstats, just so we check it. Right. Okay. Oh, it's actually, look, it's reusing the map that we had. Right. Because there is a non-zero number of packets. The parser function will parse the Ethernet header, do bounds checking, and return the next header type and position. However, there is a bug in the bounds checking logic, so the program will be rejected by let's try to load. So, are we in the right place? All right. So we have make tload is going to essentially run the XDP loader with the correct arguments. Right. Failed to load program XDP packet parser. Where's our guy? Right, here it is. Here's our guy. Yeah. The bug is in these 3 lines of code. It's in the if statement. They're giving us too much information. In parse, make sure that the problem. All right, let's read what the code is doing first. So this is again a single file can contain multiple BPF programs. So, well, in this case, it contains a bunch of stuff that I don't care about, but this is what we care about. This section is labeled with the program name. So XDP packet parses was what actually gets attached to the network interface, right? All right. And it gets the context on the enters. Then we cast the pointers to make the compiler happy. Then we have our struct. What is this type? We define it for, what is it? Oh, where are you? The fuck? Yeah, so it probably comes from the BPF helpers, right? Default action XDP pass, imply everything we couldn't parse, or that we don't want to deal with. We just pass out the stack and let the kernel deal with it. All right. These keep track of the next header type and iterative pointer. The next header type. Let's look at the type. Void pointer. Oh, I gotta fly over here. Start next header cursor position data start. Good. Packet parsing in steps. Get each header one at a time. Aborting if parsing fails. Let's see. Another person has been asking me to start for so long, and then 35 minutes later he hasn't joined yet. So anyhow, let's look at the parser helper function. So these lessons are good because there's a lot of helper stuff written for us already. Packet parsing helpers. Each helper parses a packet header, including doing bounds checking, and returns the type of its contents and is successful, -1. Otherwise, For Ethernet and IP headers, the content type is the type of the payload. The content type is the type of the payload. Let me think. Okay. For ICMP, there's the ICMP type field. All right. All the return values are in the host by OR. Very nice. We got it in the host by OR. Oh, I think actually the first time I was playing around with Rust, I was writing some BPF code, BPF compilable code in Rust, and I was trying to do like simple firewall. I wanted to block some packets coming from a particular IP address, and it took me an embarrassingly long time to figure out that bytes come in the wrong order from the network. So I needed to flip the IP address, hard coded, it had to be blocked. So, all right, let's take a look. So we got the I do not like C. Byte count bounds check. Check if current pointer plus size of header is after data. Check if current pointer plus size of header. What is this? This does not look like the size of the header. Is this the problem? No, I think they told us that. What? Get each header one at a time. Worry about it. Go-to statements are bad. Don't use them. All right. The offset is outside of the packet. Right. So my feeling is, shouldn't we use the header size here? What? Oh. No. What do you think, Genial? Oh no, they told us it's the one. I'm pretty sure it's this. It's pretty intuitive that it would be this. Oh, it did. Oh, lol. I think it just that the program didn't save. So, what is the goal of this filter again? Well, yeah. Eventually, over the course of the assignments, which show these, there are 3 steps. We're gonna block ICMP packets, but every other one, not everyone, every other one, and let the rest of the stuff through. And then first assignment was just they asked us to fix a problem because the code was not compiling. It was not compiling because this if statement here was not correct. So we're trying to check bound checking if current pointer plus size of header is after the data end, but they had a bug over here. Intentional bug. So this is the current, what are they calling it? Cursor. All right. And this is the header size. And we check if the current is under. Okay. All right. Oh, I see. Data. That's interesting. Okay. Size off. Let's try. All right, let's look at the second assignment. So we did the first. Although I'm not sure I understand. Ah, wait. What? Oh, right, I'm an idiot. Okay, now it makes sense. All right, so we got the if header struct over here. Okay. All right, and we get its size as the header. All right. Now that our Ethernet parsing program runs, we'll add parsing of the IP header. So we got the Ethernet stuff. We'll add parsing of the IP header. To do this, implement the parse IP6 header. Ooh, oh yeah, we're using IPv6 function that has a commented out product below the parse. The function will be quite similar, but you'll need to look up the IPv6 header structure definition. No, I don't want to do that. No, I hate C programming. No. That's what we're gonna do. All right. Always in line, int parse IP6 header. We have the cursor, we have the data end. Cursor is our current position, and this is where we return our stuff. Alrighty. Cool. Network byte order. So I'm gonna no. We'll need when you add bounds checking, notice that the style used in parse, which computes the size of the header, thus byte-wise comparison is not the only one possible. Which computes the size of the header and does, but right. You can also use pointer arithmetic style comparison. Sorry, gotta check something. Which makes use of the fact that the increment and pointer will move the memory is pointed to by the size. Right, yeah, of course. Isn't this will get you a bounce check that looks like this? Yep. Well, I see what they did there. I think. All right. Do I see? Okay. Oh no, did it not work? Oh yeah, we need it to force. All right. Oh. All right. Okay. Cool. Okie dokie. So what are we gonna do here? I'm gonna need to 6 to H. Boom, 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 we'll just do it this way. There we go. Right, this is our guy. Yep, it looks like our guy. Next. All right, here's the next header. Okay, let's do this. Struct. Right, and whoa. Yep. Yeah, we're doing the same stuff here. And again. Well, wait. No. Huh. What? Oh man, I'm so bad with C. It's embarrassing. All right, let's just try doing the same stuff. Because yeah, I don't IPS6 equals IPS6 Oh, whoa, I kind of missed all this. When did this happen? All right. Nope. What? Since pairing on the data field when we use it. Oops. packet type ID field. Type. eBPF target selects the Indian, so the CPU compiles on or the user specifies respectively. The user is defined by the compiler. We can rely by libc. So the actual request byte or which use different targets. Okay. Oh. Right. So we'll just get the type from here, and then from here we'll get I just I'm an idiot. The type of the payload. Let's look at this. Right. Where's our stuff? Return. Right. Okay. Cool. All right. It makes sense. So we're gonna return IPv6, right? This guy. What? No member name post. What? Line 53. Unused function? Well, who cares if it's unused? Gotta still compile it. No, I don't want. Oh. Unused function. What? Function that are declared as static. Ooh. These functions are only accessible in wondering whether they're used in the program. If you don't run these functions are known to be unused and the warning is generated. Turn off error. Alright. How do I? I'm not your new high. No, I want to disable. What are you doing? XDP targets. Oh. Oh. No, 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 no. Let's see flags. No. What? All right, we don't have any other problems other than the function being unused. Let's just remove it from being static. Let's just, and it compiles. So where's the loader? And it does load, so it works. All right, so we know that it's fine. Right, let's look at the code once again to understand it a little bit better. And let's also look at, all right, what are we doing here? We have our cursor, which I don't really get how it's being used. How's it being used? Or maybe it's not being used yet. All right, that's a good thought. It's not being used yet. All right, we have our cursor, we have data end, right? So we get the cursor, we get the struct IPv6 header, we get the header size, that's correct. Then we look if we the cursor plus the header size is over the data end, then we are in trouble. We don't want to be in trouble. So, but if we're not in trouble, then we move by the header size in our cursor. We get the return struct when we edit this, and then we return the next header value. All right. The type of its contents. All right. Note that we can successfully parse packets down to the IP header. We will not need to add parsing. Let's add static back here. What are you doing? We'll need to add parsing of the payload that we're interested in, right? For instance, the IPv6 header. To do this, implement the parsing. All right. I'm gonna do whatever you tell me. Anything. 3 viewers. Who are you? What's going on? To do this, after parsing IPv6 header, it's finally time to make our decisions based on the packet payload. I agree. In this case, we're interested in the sequence number. Oh, because we want to drop every second packet. So smart, so clever. The data structure is quite deeply nested, but the header file also defines a convenient alias. So the sequence number. Whoa. Okay. Byte order conversion. How do I make sure I have byte order? Network to host, and I want network to host, right? Let's look at how other people are using it. Here's how they're using it. So shouldn't it be less? Shouldn't it be this? That's my theory. That's my theory, right? You know what? How we can check? We can check very easily. Check very simple check. What we're gonna do is, so if we so it's not Ethernet. It goes to out, so it does the default action, which is pass, right? But if it is Ethernet, it's by default drop. So if this is correct, then it's going to be dropping it by default. And let's comment this out right now, because it's going to be complaining about static bullshit. Let's do this, and let's test that the byte order is correct. So we're gonna use our loader. Go away, go away, go away, go away. All right, success. It is getting dropped. It's getting dropped. It's getting dropped. It's getting dropped. And once again, that means that the byte or at least here, is indeed correct. Wait, no. It says network byte or. Why don't we need to? Ah, because we changed it here. I don't like this. I don't like this notation. That's very. I can't read. All right. We're gonna, like normal people, we're gonna be returning, what is that? Network to host order, right? Network to host order, correct? NTOHS, NTOHS. Right. Remove this comment. Whoever wrote this stuff doesn't know what they're doing. That's, of course, it is a lie, but all right, should still be working the same way. What? Line 45. Line 45. Line 45. Line 45. No, it's not BFP. It's BPF. Make. Line 70. What? Make. What? Oh. Cool. Let's try this again. Okay, works. Perfect. Beautiful. Now what we're gonna do here is do BPF again. All right. Way more intuitive. The helper functions should always return stuff in the host order. Otherwise, it doesn't make sense. You gotta have beautiful interfaces, you know. What's next? Parsing ICMP with 6 header and reacting to it. Now we'll need to add parsing of the payload that we are interested in. For instance, the ICMP with 6 header to do this implement. After parsing the ICMP with 6 header, it is finally time to make our decisions based on the packet payload. In this case, we're interested in the sequence number, the data structure. Right, we've read this before. With this, we can finally implement the drop logic mentioned above. Simply return an XDP drop if the sequence number is even and the XDP pass is odd. Where is our? All right. What's the return value? Int, because we're gonna return. What are we gonna return? We're gonna return the sequence value. Is that correct? That is my understanding of the situation. Let's look at the header definition. Okay. Oh, there we go. Where are you? What? 3 matches. There we go. All right, this is our guy. Type code checksum. And what are we interested in? This is the deep nested structure that they're talking about there in the explanation. What? Do I need this? I don't need it. Need to add parsing of the payload that we're interested in. You know what? I should check the value of the next header here, but what? Oh, right. I'm gonna look at the solutions very briefly. Notes our early exposition to the XDP. No, we're gonna look at the very. Which one are we doing? We're doing kernel. All right, where's our guy? Oh, shot. Boom. Parser. We don't have parser file. Okay, it's too simple. Right. eBPF. TCP. IP type. IP type. What? No. Let's look at this. This is IPv6. Next header. The type of next header. Field usually specify the transport layer protocol used by pack. What should it be in our case? Right. The transport, but this is. So should it be? Oh, there we go. All right. Now I get it. So there would be. Oh, I see it. Did I change something? All right. Now we're gonna do this. Parse. We're gonna do again nh. This is correct. Yes. Now I see. This is why we're doing the cursor thing, right? Because we're moving the cursor by the headers. Okay, now it makes sense. And we don't. Right. Okay, it's all coming together. It's all coming together, but we're gonna use this guy. IPv6. IPv6. If not equal. All right, so this is the guy what we need. ICMP. Where's the we need the no, we don't need your solution anymore. We figured it all out. My friend got a call from the manager. All right. eBPF. Dudes. ICP next. Oh, there we go. All right, this is the guy we need. Dude, hey dude. So again, if this is not ICMP-v6, we go to out because we're interested in, and the out is the default action with XDP. All right, let's make it. Make this. Who is non-void? Does not return a val. Who? 70. We don't need you. Reporting you. You look like a hacker. I'm being harassed on the internet. Oh no. University of Illinois. Hackers don't wear shirts. Although, I guess I'm a hacker. Right, we got it made. All right, it works. We can even do tload or loader. And yes, all right, I understand what we're doing now very well. very well. So well, almost too. Whoa, did you see that lag? That was insane. What are we doing on the battery? Doing fine, we got enough time. All right, struct ICMP 6 header, ICMP equals, and they, oh, it's a lot of copy pasting, you know. All right. 6 header equals ICMP return BPF ICMP. I forgot. I didn't look. What are we interested in again? There was a hint. We're interested in ICMP sequence. 6 sequence. What? Whoa, that's a lot of lag. When you pay $2,000 for a computer and it doesn't work well, isn't that funny? All right, ICMP 6. All right. Where's the sequence? What they talk. Don't forget the, all right. Return, yep. And this is, well, all right, we got November post, and no, I didn't mean post. I made the same typo again. November post, and again. Too much typo stuff. Whew. All right, cool. And now we do our actual checking. This time it's not header types. So we're gonna do sequence. Sequence equals parse ICMP6 header and data, and we need again this stuff. Struct ICMP header. The type is here. I wonder if I can play music on Twitch. Does anyone know? The millions of people who are watching. I might. I would appreciate your advice and be whether I'm able to. No, we called it ICMP. If sequence %2 is equal 0. It starts with 0 probably, but we're gonna, go to out. We need our quotient group here. That's isomorphic to this. All right. Let's make it. Whoa! It worked. Actually, right. We can actually test it now. So every second package should be coming. Wait. That doesn't look like every second packet is coming through. So see, everything is getting passed. No, I'm not gonna. No. What is it? I'm getting hacked. You can send the phishing link. What is it? I agree to all terms. Oh, no copyright music. Nice. Good game. Well played. Right, so it looks like the sequence number is not correct. Why is it not? Whoa, 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 whoa. Whoa, 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 whoa. So it's not dropping anything. It should be dropping it. Wait, wait, wait. Ah! Well, I want to pass the odd drop. You know what? Let's just try to drop it all. Will this work? Ah. Did I run Mike? What? Does the program get attached? I'm worried that the loader is not doing something correctly. You know what? We're gonna XDP unload. Alright, this is what we're gonna do. And alright. No, I don't want to know what is XDP. No. Ah, alright, there we go. IP link, set device test XDP off, sudo. Alright, and now we're gonna do tload, and now we're gonna clear. Why is it working? It should not be. It should be failing. All packets are passing. They should be being getting dropped. What? What are you returning here? What if it's returning? What if it's returning -1? I can see chat well. Oh. Why is the ICMP sequence? What? Two people are watching this. I need advice. What do you think is not working? Why is it not working? So it should be dropping some headers. According to my knowledge, it should be dropping every second ICMP header, but it's not. What if I change? You know what? Just to sort of test it. Let's do this. What was it? All right. Now it's getting dropped. Okay, so all right. How would you debug this? How do you debug this? If let's do this more explicitly. XDP drop. And then, no. Oh, why is it? It's all passing through. It's all passing through. No matter what I do here. So it's like, why is this always in this condition? Wait, what if I do 1 equals 0? If 1 equals 0, what? Too much stuff. Oh, does that mean we're going out earlier? Why am I so dumb? That's what it means. That's what it means. All right. So that's not what we're gonna do. All right. What is going on here? I feel like we're go to out here, right? Cause but it should be ICMP with 6, shouldn't it be? Pretty darn sure it is. Wrong. Oh, this is making me feel very, very dumb. By simply return. Okay. Why is it so? All right, let's check that it's let me make tload. Let's ping tstats. It's all getting passed. So this should Huh. Maybe, you know what? Maybe this is incorrect. That's what I'm thinking. The way we're gonna test it again is we're gonna do this. Oops. Alright. I'm gonna remove static so we don't have compilations issues. Ever again. Gonna do. Alright. Now we're gonna understand what's going on. T-load. Alright. And let's ping. Alright, it's failing. Okay. So it's failing, that means we're hitting equals. So this is correct. We're getting the right stuff here. Okay, let's go one more. One more. Because it should be getting dropped if it's the Ethernet header that we expect. It should be getting dropped. It was getting dropped. Okay. So now we're testing the IPv6. All right. T-load. And now, right, we're at zeros. Okay, it's not getting dropped. Okay, it's not getting dropped here, so. Whoa! Who wrote this? Why is it? I'm an idiot. No. It should be less. So this is the thing that doesn't work. This is the condition that doesn't work. Doesn't work. Why does it not work? What is it equal to? Do we convert it to the right order? We do. All right. IPv6 next header. Next header. Let's look. No jumbo list of IP protocol numbers. 1. What's it equal to? So it's see. Maybe. That's very. What if I want to v4? Where is this defined? No. Oh, there we go. There we go. There we go. All right, let's try this. What? Why does it still? What is it then? What would it be? We got trouble. We got trouble. Oh, this seems so. Is it -1? Let's do less. All right. Very clever debugging with Ilya. What am I doing? All right, now it's getting dropped. Okay, now it's getting dropped. So the return type here is actually -1. Now, why is it? Header size I see. Oh, let's see. Right, so this is returning -1 here. Why is it? Why is it? So this thing doesn't work properly. All right. Let's look. You know what? Let's look here. What? Nope. Wrong place. There's parse. Oof. No IP header. All right, parse IP header. This is what I see. Well, I mean, parse IP. So it's -1. Oh. Oh, it's not. I guess I'm bringing that today. Looks like it. It's not gonna drop. Okay, so it is something different. Yeah, but this is TCP. Okay. Yeah. Should be less. Pretty darn sure it should be less. Uh-huh. Uh-huh. All right. Yeah, let's call this if type. What is that they call it? Ping ICMP type. Ping packet structure. Set to 58. ICMP 6. 58. And I do wait. We've done the conversion of. Does this cause problem? Is it because of less? Is it because of less? No way. No way. No way. Order conversion. Always getting it wrong. Ha! Ha! Oh, terrible, terrible, but now it's correct. Let's understand why it's correct. Why is it correct? So what if we do it twice? What network byte order conversion twice? How does it work? HTON C++. Right. Let's read about host to network translation. Make sure is correct for net. Is eventually keep an eye out of for him. What happens when it's called? Well, the internet. Well, okay. For some obscure reason, that didn't work, and I'm not sure why. But now I guess it does. Right. Let's check it once again when it does. make tload and tstats, and shit is getting dropped, because we're dropping if it's ICMP, right? If it's ICMP of either type, and honestly we should just leave the ICMP with 6, and we drop. So let's be super sure about that. So, and I am 100% sure. All right. So now we're gonna do this, and we don't need ye. We do need ye. We do need we do have sequence over there. All right, let's clean it up just a little bit. Let's just go here and then here and remove this and get the indentation right, and that should be it. And then we're gonna do make, and then we're gonna do this, and then we're gonna do this, and then I'm gonna do this, and what I'm gonna see is I'm seeing every second packet getting dropped. Exactly what I wanted. Exactly what I wanted. Right. Half the packets, half the ICMP packets are getting dropped. We only have 24% of charge left. So I gotta finish this. We have one more problem to solve. Oh, it looks pretty tedious. Oh, more. There are more problems. There are 2. Right, let's see. Now we have the basic functionality working. We can improve it to also correctly handle VLAN. Whoa. Easy. Wait. Why do you use... So use network to post-order conversion here, but... Wait, did I just do a typo? Alright, let's go back. What was the problem, really? What was the problem? No, it was... I don't understand it. I don't understand. Why was this problematic? Why was it problematic? Right. Alright, this is what we're gonna do, and we're gonna make it static again because we're very cool and all that, and alright. I don't need you, I do need you, and the fix. Alright, and then remove this, and again, make, alright, we're good. Alright, let's do the next one. We can improve it to also correctly handle VLAN tags and the Ethernet packages. Whoa. How to parse multiple variable headers depending on the payload. Linux VLANs are configured by creating virtual interfaces of type VLAN, but since the XDP program runs directly on the real interface, CL packets with their VLAN tags before the kernel assigns them to the virtual VLAN interfaces. Let me process the sentence once again. Multiple variable headers depending on the payload. You can use this to create a parser that will work with any VLAN encapsulation. So you'll know the hardware offloads below. It's to see the VLAN. It's important to turn off VLAN hardware offload, since this will remove the VLAN tag from the packet header. Yeah. All right. Let's look. VLAN tagging. Virtual trunk links are physical. All right. Uh-huh. All right. All right. So we need to VLAN, okay. Ah, uh-huh, 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 uh-huh. And we just want to parse the VLAN tags and we find the encapsulated P header. No, edit and removing the VLAN. This means that we can, wow, we can do a lot with XDP. This is a really powerful tool. All right. This means that we can just augment the parse, if header, conditional parse VLAN tags. Just take a minute to parse. Or do tags are files. All right. Alright, alright, alright. Uh-huh. Good, 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 good. Good, 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 good. Alright. The single packing has several VLAN tags can unlock roll loops. VLAN TCI. Tag control. Wow, that's pretty dope. Alright. Um cool. So how do I do this? If now what do we do? Should I be doing this before this processing? But then yeah, pretty sure it should be. Alright. If product is VLAN, the stuff, then what do we do? And then I like that they call IPv4 packets legacy. That's the right way to do it. The final assignment for the session is to extend the problem from 4. The only complication to be aware of is a variant size. We'll need to do the bounce checking 2 passes for structs fits in the packet payload and compute the actual header sizes. Finally verify that this full size fits in the packet. Alright, I get it, but we'll need some help with the VLAN thing. VLAN thing is getting under my skin, so I'm gonna look at this. Proto is VLAN tag pop, otherwise push. How do you pop? Ooh, 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 ooh. That's interesting. That's not exactly what I want to do. So, okay, they're doing the same stuff. Oh, they're doing the, I see. Break otherwise. Break otherwise. This is the stuff that we need. Okay, it's not very hard. So, okay, so we first process our stuff as normal. Right. We got this, but then we actually do VLH, which is gonna be, right? What? VLAN header VLH. Alright. Where's this thing? H equals, what are we doing? Alright, the current position. Right. H pro, yep. Alright. If where's this function? If proto is if h proto return BPF. Oops. Now we do our normal return, aka this. Else, otherwise we do if VLH plus 1 data and return minus 1. Alright. Ariel, how are you doing? Now everything is passing. So we're returning something around here. Something's wrong. Something's wrong. What's wrong? Okay, let's return. So let's. Alright, so it's hitting this path, which is correct. Now it should be returning. Just like we did last time. And this should work. Alright, it does work. But otherwise, we should be. Yeah, this doesn't make sense to me. Where are we? Yep. Same stuff. Ah. F. Alright, and what else we do return Alright. Alright, it works. Okay. It works at least in the old scenario, and alright, we have 11%. Let's see. Let's all the virtual machine doing its shit. Now we're gonna do t reset VLAN. Oh, come on. Alright, and it looks like it worked. If config. Ooh. And tstats. And tping VLAN. Right. Tstats. Oh. Make IP. Okay, it's all passing. Something's wrong. But you know, this bug with the VLANs, I'm gonna figure out tomorrow, because otherwise it's gonna be too much and the laptop is about to die. What we're gonna do though is add some support for IPv4 real quick. It should be pretty simple. T reset cool if config cool IP. All right. That's fine. Okay. Let's quickly do the if IPv6 equals all right, this is just basically refactoring it that I'm gonna do tomorrow or in the morning. That is correct. All right, so what we did today, we did some packet processing with XDP. So last time we just learned how to load maps and show statistics and whatever, but this time we actually do packet processing and we're not letting in any every other ICMP packet, and we ignore anything that's not ICMP, so that's pretty dope. What I got to do is add some support for VLANs, which I need to understand a little better, so I'm gonna go read a textbook on this, and we need to add support for IPv4, which is legacy. No one's using IPv4 anymore. It's 2020. It's 2021. And once that is done, we're good. All right. That should be small homework for me to do later. And then I'll move on to the next task. This was a fun one. I need to read up a little bit to get the full mental picture, and that is good. All right. How do I end this? I click the end stream supposedly. So goodbye.